Yeah, we're trying to reset it now, Ro, to see if it helps, and I can see already that it's not helping. Clearly, this is one of those streams that just wasn't meant to be.
Yeah.
It seems like it might be slightly better now. What do we think?
Does seem a little better.
Yeah, are we back? Alright, we'll soldier on a little bit. Yeah, it's definitely one of those nights. Okay. So, looking at the code, and I'll share it on Discord as well. Okay, are you receiving that now? Can you see it?
Good. Yes.
Alright, so let's first of all, let's think about the x coordinate, right?
Yeah.
So we'll worry about the y coordinate later, because the y coordinate is more complicated than the x.
Yeah, I can imagine.
But what we can see from the x coordinate, right, is if you look at that display there with the lines on it, yeah? The first thing, let's look at the actual pixel pattern, right? So you know, as we go from one pixel to the next, the first 8 pixels. First of all, you need an address, and then you need the pixel pattern itself, right?
Yeah. One sec.
So,
the washing machine's making a really loud noise. I'm going to shut the door.
okay. We're getting everything tonight.
Yeah.
So you remember from yesterday, right, that if you're going to print a pixel within a byte like this, then you're going to basically use a different pattern for each of 8 different pixels, right? You remember that?
Yep.
And the first one is 128, yeah?
Yeah. Yeah.
And then this one is 64, and this one is 32, and so on, right?
Yep.
Okay, and then to go to the next pixel, the next one along, we would go to address 4001, right?
Yeah.
And then we would go back, and then we would be back at 1, like that again, 128, yeah? I think there's literally just you and me and one other person now. Everyone else has given up because of the lag. Who's the one person that stayed? Speak up. Probably a bot. Well, listen. You know what? What I mean. What are your plans this weekend? Hey,
This
Tails.
weekend I've got to go shopping for some holiday stuff.
I see, but I mean, at this time of day, are you about or?
Probably not, because I'll probably be over at Bernie's.
Mm.
Weekends are a bit up in the air, really.
Every weekend is a weekend at Bernie's, huh?
Trying to get it working on the other laptop at home.
Well, Tails is still here, so. Okay, let's summarize at least how we can plot an x coordinate from 0 to 255, right?
Yeah.
Okay. So, in order to plot something, a single pixel, we're going to need two things. We're going to need the memory address, right?
Yep.
And we're going to need the pixel pattern byte.
Yeah.
Right? Because there are 256 possible pixels, and there are 32 memory addresses on that very top line, right?
Yeah.
Okay, so how do we do it? Well, the easiest way to do it, first of all, it's easy enough to find the byte, isn't it, right? So because you know that, let's say your x value, give me any random x value that you want.
Well, let's go 16.
Okay. Well, let's pick a slightly bigger number, something, and maybe an odd number or something as well. Just make it more interesting.
Oh, you mean out of 256?
Yeah.
Oh, 137.
Okay. 137 it is. Yeah. Okay. So it should be pretty logical and clear that if I want to know which character square to put that in, yeah.
Yeah.
All I need to do is divide it by 8, right?
8. Yeah.
And so dividing by 8 is a pretty straightforward thing. So we had 137, right?
Yeah.
And which in binary would be that 1000 1001. Yep.
Yeah.
So we know division is easy enough. We can just use a rotate or a shift. So if we do something like rotate to the left, or rotate to the right 3 times, that would divide by 8. Yeah.
Yeah.
Now you got to be careful though, because if I do rotate this, then the end result would be that these 3 numbers would end up over here, right?
Yeah. Yeah.
So actually what we really want is that we only want this bit here, yeah? We don't want this bit.
Right.
See what I mean?
Yeah.
So what we can do is we can do a mask on it like that. See what I mean?
Right. Yeah.
Does that make sense?
Yeah.
Are you fairly comfortable with that now?
I think so, yeah.
That's a basic division by 8 formula, right? Now, you can use a shift. You can use shift right.
Okay.
But I think, and I'm not absolutely sure here, but I know that this is quicker than shift right, and it could well be that if you do that 3 times, and then you use the and, it's actually quicker than using 3 shift rights.
Okay.
In general, RRCA and RLCA are really quick, right? So,
okay.
Yeah, so you just mask it off, right? And that would tell you, you know, from 0 to 256, that would give you a number from 0 to 31, right?
Yeah. Mm.
Yeah? From 0 to 255, then you divide by 8, that's going to give you a number from 0 to 31.
Right. So we're only doing the 3 rotates because we're taking 137 up to 140, yeah?
Sorry?
Why are there 3 rotate?
Oh, well, we want to divide by 8, don't we?
Yeah.
So divide by 2. Divide by 2 again.
Oh, I see. Sorry, yeah. Gotcha.
And divide by 2 again.
Right.
See what I mean?
Yeah.
2 times 2 times 2, 8.
Yeah, right. Yeah.
2 divided by 2 divided by 2 would be 0.5 or whatever. Anyway, you get the idea.
Yeah. Yeah. Okay.
So, any division by 2, 4, 8, 16 is dead easy and quick. So we try and keep to that wherever we can. So that basically gives us the first 5 bits that that we need for our x coordinate. Yeah.
Yeah.
Now it gets a little bit complicated, of course, because if you look back at this, you'll see that, of course, it goes down. So here it's 0 to 31, but here it's going to be 32 to 63, right?
Right, back on the other screen. Okay.
Sorry, yes. If you look at the well, I'll replicate it on here for your benefit as well, right? Okay, you see there are 32, that's 32 bytes, right? With lines across like that, yeah?
Yeah.
Okay. And there are 8 of them. Yeah?
Yeah.
And because we're dealing with 8-bit numbers, so the numbers here go from 0 to 31.
Yeah.
And then
here,
this is the low byte, of course, right? That's going to be 32 to 63, and that's going to be 64 here.
Yeah. Yeah.
And here it's going to be 95, right?
Yeah.
Like that. And all the way down. And the last one here will be 255.
Yeah.
That's the low byte, yeah?
Yeah.
So the difficulty that you've got here is that, of course, if you're going to plot on here, it's easy. You can just divide by 8, right?
Yeah.
To know what the x should be. But once you go above that, you can end up in a bit of trouble, right? Because it's a bigger number.
Right.
But I think the mask will help us with that. But then, obviously, we might. What I mean is that the low byte for this one here, let's say, is not going to be the same as the low byte for this one. It's going to be 32 more, right?
Yes.
In other words, the low byte is a combination of something from the x coordinate and something from the y coordinate, right?
Right.
And so this part of it is the x coordinate, and this part of it is going to be the y coordinate, going to be affected by the y coordinate, you see?
Okay.
But let's not worry about that for now, right? Let's just go for the first line, and then we'll worry about the rest later, yeah?
Yeah.
Okay. So let's bear in mind when we start thinking. To be honest, it does become a bit clearer once you kind of get your head around it. But the most common way of dealing with it all is just to use like a lookup table so that you can find the addresses quickly.
Yeah.
But there's no harm in kind of learning how it works, because obviously if once you've got a good handle on the way the screen memory works, then you know it makes everything easier really when it comes to like printing stuff or whatever. Okay, so if we want to plot on that first line, then it's easy enough. It's 0 to 31, right?
Yeah.
And then we've got, and this is what we'll finish up with today, because you know it's not really been. Oh, we've got a new person's come in. I want to welcome. I don't know who's come back, but whoever you are, welcome back. Please say hello. We had a stream went down and we lost almost everybody. So yeah. Anyway, so that's the we've isolated the address, right, of the low byte, right? The high byte's not going to change because we're just dealing with the top line anyway, right?
Yeah.
And incidentally, actually, because we know with the high byte we can just add 1 to the high byte, we're actually dealing with not just this one line, but the whole first character row. See what I mean? So you remember how we go down one single line within a character?
Yeah.
So for example, there, if we go across one, it's going to be like that, right? And if we go down one, it's going to be like that. Remember?
Yeah.
To a maximum down to 7. That's within that character, right?
So, yeah.
So essentially, that means that within the sort of 8, we've got 8 characters, and we've got 32 characters, 32 across and 8 down, right? So within that area of pixels, there are 256 pixels, and we can actually we could determine the x coordinate of any of those, because they've all got the same low byte address within from 0 to 31, and then a different high byte address.
Right.
Does that make sense? I hope so. Well, look, we'll demo it anyway, right?
Yeah.
Okay, so, and then to determine, we're literally just going to think about that top line for tonight, and then we'll think about the rest later. So we'll go to here. We'll divide by 8, and that gives us these bytes here, which is enough for us to know the low byte of our address, right?
Yeah.
And the pixel pattern, obviously, is what we actually write to that address.
Yeah.
So in this case, the pixel pattern, the easiest way to do that is to actually use a lookup table. So for example, if I put a lookup table like this and I say pixel pattern, right?
Yeah.
And I say def b 1 to 8, 64, 32, 16, 8, 4, 2, 1, right?
Okay.
Now, let's say then that we want to. If we then look at the x coordinate, right? It's going to go 0, 1, 2, 3, 4, 5, 6, 7, right? Inside one character.
Yeah.
So, and then obviously the next one would be 8, 9, 10, 11, 12. So you remember it's the same repeating pattern again, right? So when you look at the x coordinate, let's say our x coordinate here was what did you say? 137. It was something like 1. That was it, wasn't it? Yeah.
Yeah.
So if we look at the first, if we look at the first 3 bytes, yeah, that's always going to be, that's going to be a number from 0 to 7. Clear?
Yes.
So essentially, those 3 bytes will always be, if it's, it'll be 0, 1, 2, 3, 4, 5, 6, or 7, right?
Yeah.
And so all we have to do is match that up with this: 128, 64, 32, 16, 8, 41.
Yep.
See what I mean?
Yep.
So, yeah, it's tricky on the stream to sort of line this up with. I'd like to use. It seems, well, the stream seems to be a bit better now, doesn't it? But
it does, yeah, it's not too bad.
I'm definitely not. I'm not 100% now. I'm tired, and as I said, I was ill, so I feel like I'm not really doing the job that I normally do this week. But it does happen.
It's fine.
Anyway, so all we wanted, so what we want to do then is if we're gonna plot. Okay, let's look at it like this, right? The very first address, right, is at 4000.
Yeah.
Okay, it's right there. Now, if we want to plot at position 1, sorry, coordinate 0, right? Then we'd need to poke it with 128, yeah. And if we want to at coordinate 2, we're gonna poke it with 64. See what I mean?
Yeah. Yeah.
So essentially, then all we have to do is line up that this is like we've trimmed off the pixel, these 3 bytes here, right?
Yeah.
And that will determine the value that we use for our pattern, right?
Yeah.
Now, what's interesting about that, as you'll see, is that in fact, if we look at these 2 pieces together, right, you'll see that this is the piece that we used to determine which character square to print on, right? Because we divided by 8.
Right.
You remember?
Yep.
So it's actually there 0001, and that is this part here is that there, yeah?
Yeah.
And this part, in this case, tells us the value that we need to sort of poke, if you like, into memory from 0 to 7. And what we need to do then is we need to kind of convert this into that.
Yeah.
Now, you could probably use some kind of complex fiddly maths to do it, but it's much easier if you just use a table and look it up, right?
Yeah.
Okay, so let's talk about how we would do that. So let's go back. It's always a lot easier when you actually do it on a practical level, isn't it? So
yeah, it is.
Okay, so I'm gonna scrap all of this because we're not going to use any kind of a loop this time, right? We're just going to plot at a particular position. So to start off, let's use what we already know. So let's say okay, I'm going to put something here called my x, right? And we'll set it at, for now, let's do 0 to 7, right? So we'll call it, say, oh no, sorry. Let's start it out. Okay, we'll call it 137, right? that's your sorry, def b. That's going to be your value of your x coordinate. Yeah, you with me?
Yeah.
Okay, so what we do is then we'll load the value of x coordinate into the accumulator, right?
Yeah.
And then we will RRCA 3 times, rotate it 3 times, and then we'll AND it with this. And you know, you can of course use the hex or the decimal. You know, I'm mainly using the binary just so you can actually see what's going on, right?
Yeah.
When you're in the habit of it, you're quite used to using something like AND 31 or AND 1F, you know. Like, let's say AND 31. It just means cut off the first bit and okay. And then what we'll do is we'll say, because we know we're only on one line, we're not going to cross over anything. So now we'll say add A to L, right? And then load L with A. Do you see what we're doing there?
So 1. So you're just adding 1 to the accumulator and then.
Well, look, there's the screen address. There's the screen address of the top of the screen, right? That's my x coordinate. Divide by 8.
Yeah.
Mask off. And then I'm just going to add the result to the original value here. So it's going to add to this. And then once it's been added, we put it into the address so that the address will now be whatever the result of that is. Yeah?
Right.
And then for now, I'm going to load HL with 255 just for demonstration purposes, right? Which is all 8 pixels.
Yeah.
Now, just to show that working, hopefully this is enough at least to show the basics of that. If we go back to Spectaculator, right, we'll load that in and we'll run it. Okay, now I'll wait for the stream to catch up. Wow, it's really laggy, isn't it? There you go. Right, so what I'm going to do from now on is when I do something on Spectaculator, I'll start explaining it when it actually appears so that everyone's caught up. So that is the character, that's the screen address of where pixel 137 would be, right?
Right.
I mean, it's not just pixel 137. There are another 7 pixels that also inhabit that 1 byte. Yeah.
Yeah.
But for now, that's the correct one. So if I go, you'll see what will happen is if I change this to 138, right?
Yeah.
I think we'll get exactly the same result. Same result because it's still in that same character square, right? You just wait a second. There you go. Right, same result. It hasn't changed because it'll only change when it goes off the 8 in a chunk of 8 pixels into the next address. You see what I mean?
Yes. Yeah.
So that would be what would it be? I guess 128, 136. Oh, it would actually be 144, I think, right? That's the next one that's divisible by 8, isn't it?
Yeah.
So if I run that now, then we should see that it'll change. No.
Cheers, Towser.
Got to shoot. Okay. I don't know who else is here. Just one lurker that isn't speaking. We're gonna finish up in a minute now. Yeah. I guess it's 1:45 then. Maybe it will take us into the next section, unless I didn't load it. Oh, something gone wrong here. I think it's my maths that's gone wrong. Oh, it should be. Bastard, how... Sorry, I didn't mean to swear so much. I don't suppose anyone really cares. It was a mosquito and I absolutely hate them, and I really did swear badly then. I apologise. I mean, it's an adult stream, I suppose. I'm so annoyed I didn't kill it because it's sure to bite me later.
Yeah, oh yeah.
Yeah, I'm doing something. Something is definitely not right here because what am I doing wrong? Something gone absolutely wrong here because it's the same address every time.
That's odd.
Yeah. What have I done wrong? I can't see anything wrong unless... Incidentally, I need to have an organ here that I haven't got. Not that it makes any difference, I don't think, but oh, actually, it would make a difference, wouldn't it? Maybe, I don't know. I don't think it will, but we'll see.
Yeah.
Oh yeah, I think it might. Yeah. What I did is I was compiling it in the ROM.
Oh.
Yeah. So what I'd done is I hadn't set an org here.
Yes.
So it was reading my-x, yeah? All this
right.
would be okay, but the my-x would have been in the ROM.
Okay.
Because it would have been compiled from 0. So now it actually works. I think. Yeah, interesting. So 137 we were at, so we'll do that. Because yeah, 137 should be somewhere in the middle anyway, shouldn't it? It shouldn't be like...
Yeah.
It shouldn't have been right over there, so that's... I think
it's just over halfway, isn't it?
Yeah, now that's better. Yeah, that's where it should be.
Yeah. So if I do...
So basically, schoolboy error, or I just deleted it by mistake. I didn't org at the right place. So yeah, and if we go to 144, that should be enough to cross that line. Yeah, I didn't think there was anything. Yeah, you see, that's one step. So
yeah, I've got mine.
In terms of the x coordinate of the top line, 0 to 7, 8 to 15, 16 to 23, and so on, right? So all we need to do then is we need to know the actual pattern, right?
Yeah.
And we'll take that from here, pixel pattern. To determine the value.
Okay.
So now we're going to have to work out the value. So we won't be loading it with 255 now. We'll be loading it with the correct value, but we need to calculate it, right? So what I'm going to do is I'm going to load, let's say, C with A. Store it for later because we're going to read something. We want to keep it so we can bring it back again, right?
Yeah.
We'll bring back the x coordinate, right?
Yeah.
Now there's a couple of things you can do here, but since we know that it's, if you look at where this is stored, right, you can see it's stored at C013 to Z01A, right?
Yep.
So the high byte doesn't change, which means that we can just use a standard 8-bit addition to work it out, right? So all I want to do is give. We'll do it this way for now, right? Load DE pixel pattern, right? So that puts this address here into DE, right? So it points it to here. Now what we do is we add A to E and load E to A, right? And we also need to, and I'll explain all of this in a minute, but then we also need to mask it off as well.
Right. It's getting complicated now.
No, it's not so bad, I promise you. Right. Okay, I'm going to revert this one back to binary so that it's clear. Okay. So you remember that within a character square, the pixel will be from 0 to 7, right?
Yeah.
And as we go to the next one, it will also be from 0 to 7, so there are 8 different patterns, right?
Yeah.
So if we mask off the first 3 bits, yeah?
Yeah.
Then that will always give us a number from 0 to 7.
Right.
And that 0 to 7 can be correspondent to these numbers here, which will give us the actual pattern itself, right?
Okay.
Got it?
Yeah.
So in order to determine where we're going to read this number, we're going to start with this address, yeah? And then add a number from 0 to 7.
Okay.
See what I mean?
Yeah. Yeah.
You sure?
Yeah, I think so. Yeah.
Okay, and that's what we're doing here. So we're saying load DE with pixel pattern.
Yeah.
And then add this masked value to E, to the low byte here. So we're just going to add, and so we're going to read which of these we need to plot.
Yeah. Yeah.
Yeah. So if it's 0, we'll be at 128 because it's the first pixel.
Yeah.
And if it's 1, it'll be 64. That's the second pixel. That's the third, the fourth, the fifth, the sixth, the seventh, and the 8th pixel at the end there.
Yeah.
Yeah? Does that make sense?
Yeah.
So now DE has the address of the pattern, right? And then, so all we need to do then is read from the lookup table that pattern and load it into the memory address that we calculated. All right, but don't worry, we'll go through it all again. We'll review it all. But let's see if it actually worked, right? So well, I'm back at 0, 0, so that obviously hasn't worked, has it? Don't know what I've done wrong there. That makes no sense at all. I'm doing my reputation no end of harm with this series of coding. Oh, he's rubbish. Look at him. He just makes it up as he goes along. Well, in fairness, you know, it is bloody 4:15, and I am.
Yeah.
I really wonder who else is watching. Is it Ro? There's one other person, and I'm soldiering on because we're almost finished. And this is just between you and me.
I have no idea.
Other people will catch up anyway. So.
I can't believe that you can't actually see who's on your stream.
Oh, well, maybe that. Yeah, you probably can. I don't know. I don't know how. Community? I don't know. I've turned off I can't even see the chat now. What have I done?
Go to the stream chat section and click on the users in chat icon.
Well, I've completely messed it up now because I can't even see the chat anymore.
Oh.
So I don't know what I've done there. Oh, I think there we go. Expand. All right. Oh, there we go. The chat's come back, but that seems like an old one. I don't know.
Yeah, I can't see. Oh, and it clears it. That's ridiculous.
So where's users in chat? I don't know where that is.
I don't know. It's an icon that looks like a person with a shadow.
Yeah. Oh yeah, I can see that there. But that says community.
Yeah, but that's not. That's.
It says here viewers. But that's just active viewers, recently active viewers.
Yeah.
Oh well, perhaps they will remain anonymous for now. Might be a bot, you know.
How to see who's watching your stream. Same thing.
So why doesn't this work? What? Oh, wait a minute. No, that should be okay. One of the things you can do when you're sort of messing about is if you just comment out certain bits of code, that's a good way of tracing it sometimes, you know.
Yeah.
Right, that's just printing it as address 0 now. Which is just wrong. That was working before. Oh, warning, value is truncated to 8-bit value. Ah, right, that's the problem right there then. You should always read your warnings. Look, that's a 9-bit number, isn't it?
I don't have any warnings. What do you have?
Look, you see what I've done? I've put a $ there instead of a percentage.
Oh, right. Right.
Yeah, you know when I restored it to binary, that's why. Yeah, okay. You see, the thing is, in my defense, I can clearly see the errors that I'm making here are just the kind of errors that you'd make if you were really tired, you know? Just little typos and things. So for everyone watching it later, that's what's going on.
Yeah, I've got mine's working. Yeah.
Yeah, so you can see, look, you plot it there, right? And if you change that number,
then it plots at the
we should, well, let's change it to any old number like 71, right?
Yeah.
And that should work fine as well. Oh, well, look, mine's plotted it down there. That's totally wrong. The mask, well, the mask isn't working. That's what that means. The mask isn't working.
Yeah, because I just plotted 255 and mine's gone down near the bottom of that first screen section.
Yeah, well, the reason is that this mask is wrong because we've divided it, right? And it needs to be that way around. That's why. We've done that. You see, you could do that. The mask that I did, you could use that mask, but you'd use it before you did the rotate, you see.
Right.
See what I mean?
Yeah.
I make these mistakes deliberately just to show you, you know. Yeah, but essentially, look, what that one does, when I converted it back, it was like, you know, 0, 0, 0, 1, 2, 3, 4, 5. I was masking off this part.
Yeah.
But what I actually wrote was this, because I'm so tired. Because this is the bit that you actually want before you divide it. But when you divide it, you rotate it and it turns into that. You see?
Into that.
So the bit that we're after is there. So these two things. But that's an interesting demo of how I can show you this. Like, so this would work. This helps you to understand a bit more about rotation and stuff. Anyway, sorry, I can't even see my own bloody keyboard now. Right. Yeah, we need to mask it off here because it's been shifted. Yeah?
Yeah.
So, you know, that'd work now. Yeah, right. So we can plot now. Anywhere on that line we can plot. And now that it's working, we can review it. But incidentally, you could do that same mask here before you did the rotate. Yeah?
Right.
And it would do the same thing because it would be masking off bits. I mean, what I mean to say is, I apologize. What I mean to say is you would mask it like that. Yeah? Before you did the rotate, it would be the same effect. It'd have the same effect because you'd just be cutting off the same bits because they've been rotated 3 times. You know what I mean?
Right.
Yeah. Was that a proper right or just a?
No. Yeah. I'm sorry. I was just typing it. I'm just trying it.
Yeah. Yeah. Do you see what I mean though? Because it's just rotated. So if you do the mask before the rotate, it doesn't really matter. You're still masking off the same thing. Yeah?
Yeah, oh, hold on. Because I don't need that. Yeah, I was just changing it, but I'm still not getting it. But what have you done there? You're loading... Why are you loading 255 into HL?
Oh, because I was just testing it to see if it would work. Just ignore that, yeah.
Right.
Yeah, just ignore that line there. That's just
okay. Right. Yeah. So mine's. Well, say mine's working. Is it? Is it working? I'm guessing I've got a border. Little border. View border.
Oh, it's lagging again.
Small. Oh, okay. It will do.
I wonder if it, when it's recording, right? Does it just, what happens when it
Yeah.
lags? Does it just include the lag,
I have no idea.
or does it like just cut it or something? I don't know. Okay, well let's summarise. Not the best of streams tonight, but it's alright. Where's she gone now? She went to sleep again. Oops. There's a certain level of trust involved with cats, isn't it? You just have to kind of be like, oh, she's probably all right.
Yeah.
I mean,
You get worried when you haven't heard them scratch or meow after a bit.
Yeah, exactly. Yeah, it's the thing is, we just moved in, and we were just kind of enjoying living together in this nicer place, and now it's kind of like, oh, what time are you going home? Yeah, just can you give us some food or this and this? It's like, oh, okay, let's just chill out. I think it's a bit much. But it's been a very useful lesson.
Yeah. Yeah, I mean, that's a decent little bit of learning.
Yeah, and look, we're doing the right thing in terms of just looking after her for a bit, and then, yeah, we'll find someone that can look after her more long term. Because we're going on holiday as well, and we've got no idea what to do then.
Yeah.
So we'd be better to just figure it out sooner rather than later.
Yeah.
But we'll keep her as long as we can until we can find someone. But she's very cute, so I think that's a good thing, because it will be quite easy. I think. I hope so. Anyway. But I will miss her as well.
Yeah.
Anyway.
The longer you have it, the harder it will be to.
Well, exactly. Yeah, exactly. So. Anyway, and she's already been moved on once already, so it's
Yeah.
I mean, technically, I suppose she should still be with her mum. She's much too young. They're supposed to be leaving with their mum until at least 3 months, right?
3 months, yeah.
And she's not 3 months. No chance. Anyway, let's go back and finish up. Make sure that you understand what we've done here, right?
Yeah.
Okay, so we're dealing with the top line. We know that the address of the top line is from 400 to 401F, right? Or 0 to 31. Each one of those 31 is a memory address. So to determine whereabouts, what we're going to poke, which address we're going to poke, we divide by 8 and we mask it off, and then we add that value to the low byte of the address, and that gives us the screen address from either, because the values are from 4000 to 401F, right?
Yep.
Be any one of those values. Now, bring back the x coordinate to calculate the correct pattern, but we're not really calculating. We're actually going to read it from a table.
Yeah.
Right. So this time, instead of looking at those 5 bits there, which of course were originally, as we said, I mean, I suppose if I put this up here, it actually makes it a clearer demo, really, because then you see that you're actually.
Yeah, it does. Yeah.
Then you see that which bits you're using. So you read in these bits here to get the address, and then you read in these 3 bits here to get the pattern.
Yeah.
Because logically, if you've got a number from 0 to 255, then you must be able to get both of those things from one number because it's contained within it, right? So and indeed, yeah. So what you have is this part is the segment, the character, and this part is the pattern. Yep. So you divide that by 8, and you'll get a number from 0 to 31, and that's your whereabouts you are on the line, on the screen address. And then this one is from 0 to 7.
Yeah.
0 to 7. A very wafting sort of fishy farty smell just drifted my way. So I think she's somewhere about. And yeah, rather than calculate that, the easiest way, because you only need 8 bytes, then you just read it off. So you start DE with this address, and then you just add the number from 0 to 7 to that address, and then read whatever value you've got in there, right?
Yeah.
That essentially is what we call a very simple pre-calculated table. Yeah.
Okay.
So when you hear something like pre-calc or lookup table, it's always the fastest way, right? It's important to note, right, that when you do that, if you do it within a how to say, you do it if you want to make sure that you do it within so that it doesn't cross a border, right? Because if it crosses over to C1, then you're going to have a problem, right?
Okay.
So one of the simplest ways to resolve that would be to put something in here like a line 8, yeah?
Right.
And that would make sure that all of those numbers were always within. Yeah, so it's going to it's aligned it to CO20, right? So it's cost you a couple of bytes, but now even if whatever I do now, if I add whatever I add to this, this one is always going to start at a number that is at least aligned within that, so that it'll never sort of be halfway through, and then it'll never mess it up. You see what I mean?
Yeah.
So yeah, you can do that, but alternatively, you can just kind of you can put it somewhere where you know that it's all. You can put it in a fixed place or something where you know that it's. Like for example, you might have some sprite data and you've got a spare 8 bytes at the end, and you know that you can just fit it in, or you know what I mean, something like this, wherever.
Yeah. Yeah.
But for now, that's probably good practice to do it that way. Yeah. So now we can plot a pixel from.
Yep.
Like that, right? In fact, so let's try one more thing, right? So we'll say we'll call that a plot pixel, right?
Yep.
Okay, and that's just here, and then we'll go load a myx, call plot pixel. Sorry, no, what we'll do is we'll just call plot pixel, right? And we'll start myx at 0, right? Yeah?
Okay.
So that will plot at 0. Load a myx, int a.
Alexa, sofa on. That's what I was doing. So, okay, so we're doing call.
Which phone number?
Oh, Alexa, stop.
Contacted.
Right. Okay, so what we do is we're going to plot the pixel. Yeah.
Yeah, so we call that, yeah.
And then we're going to load the X value.
Yeah.
And we're going to increase it.
Right.
And if it hits 0, we're going to return. Because that means if it goes to 255, and then it goes to 0, then it'll just quit.
Yeah.
Otherwise, we're going to update my X to be what we've just increased. And then we're going to jump back to the plot again. So we're going to do that 255 times. Yeah? See what I mean? And I guess we'll put a halt in there as well, just so that it doesn't go too quickly. Okay, and if you look at that now, you'll see that we've got a dot that moves right the way across the screen, but obviously we're not removing the dot, right?
What are you saying?
Do you understand why we've got that dotted line?
Yeah.
Okay, then why?
Yeah, because we're just incrementing the load by every.
Yeah. We're changing the pattern within this character square, so that's overwriting it. But as soon as we get to the last one, we're jumping to the next character square, so the previous character square is not getting overwritten. See what I mean?
Yeah.
I mean, look, I can show you on here.
Can you just run it again on yours?
Yeah, you'll need to remember the memory. I'm not sure, but I don't think the memory address will. Yeah, you won't run the second time. It's stuck at the end there. No. I'm not sure quite why that is, but.
Oh yeah.
Oh, it's to do with my X, because my X has been set to 255. You see, and it's stuck at 255. So you have to reset my X. You see what I mean? Because my X is not in the registers, it's actually in the memory, that's why.
Right.
So, you can do it like this, right? If you want to fix that, you can do this. You can start like this. Reset my X to 0 at the beginning. Yeah, there is a way that you can set A to 0 without using 2 bytes, but we'll look at that another time. Sorry, I've got errors now because of that. Okay, so what it's doing, you've got these 8 bits here, right? And it's going like this, and then it's going to here. And so every time it writes to that byte, of course, it's going to clear everything else. So that one's going to get cleared. Yeah?
Yeah.
And then when it gets to there, it goes to the next one, and then it goes like that, and so it leaves a trail. It leaves one single trail each time when it
which we had last week, didn't we? And we just set that to 0.
Yeah. This time though, we can't really do that because we're calculating it. Well, there is a way that we can. Well, there is a kind of a way that we can do it. It would be like if we know where we are at the memory address, the pixel pattern.
Yeah.
We could potentially reset it, but Yeah, but just to show you what's interesting about this is that well, instead of doing that, right, I'll tell you what we'll do. Instead of what we'll do is we'll go like this, right? We'll go load just a little bit more for tonight, not too much more, but just a little since we're here and I'm feeling it a little bit. So right, so what we'll do is okay, load. So that's an overprint, yeah? Mix with whatever's already there and then print it. So that's going to give us a straight line. You understand why? Or HL, or with whatever the value of what's already on the screen.
Yes, yeah.
Okay. And the reason that's interesting, because the reason this is going to be more powerful than the previous one, because, for example, what we can do now, as you can see from this, is that we can go like that, right? Okay, and that's fine, right? That's exactly what we would expect.
Yeah.
Now, and the only reason that's so slow is because we put that halt in there, you know.
Halt in, yeah.
Okay. But what you could do, you see, is you could go like this. You could go put 2 ink A's in there instead, right? You have to be careful because of the ret Z. You might not get a Z result, a 0 result if you increase it twice. But you should, if you start from 0 and you keep increasing by 2, you will go back to 0, right? So in that way, you can increase the value. All we're doing there is we're increasing the value of my x twice now. So now you'll get this, you see.
Right.
Yeah, because all I'm doing is I'm increasing the x coordinate by 2 instead of by 1.
2. Yeah.
Yeah, and I mean the thing is, you could do it if you did it by 3. Then you'd have an issue, right? I mean, well, I'll show you the issue because it'd be interesting to learn anyway. But if I did it by 3, right, then that ret z wouldn't necessarily work because 3. What will happen is it'll print it every 3 pixels, but it won't hit 0 anymore. It'll
0. Yeah.
Instead, it'll hit 2 or something, right? So what you'll get is you'll get every 3, and then it'll loop again.
Yeah.
And it'll probably loop 3 times, and then it'll match
it'll hit
up.
0.
Yeah. So
you
know, you could compare A to 255, and then that would work.
Yeah.
So you know, we can do that as well if you want. But right, so let's look at that now because it's a nice simple demo there, right? And look, it'll go. Yeah, you see, it's overlapping and overlapping a 3rd time before it hits the 0. Do you understand why that's happened? Yeah.
I do. Yep.
It's just because 3 is an odd number, right? It's like a prime number or whatever. Like,
yeah.
So it just won't go. It won't hit 0. But if we did this, compare 255, yeah. Well, what would we do? Let's say, well, we want to quit at. Yeah. Let's see. How would we solve that problem? I suppose. I guess we'll compare it to. What would be the last 3rd number? The last multiple of 3 would be, what would it be? 250. 250. Well, multiples of 3 always add up to 3, interestingly enough. So, always add up to a multiple of 3. So,
240.
255 should actually be a multiple of 3 then.
Probably 2.
Yeah, 255 is a multiple of 3.
Is it?
Yeah, I think so. Yeah, 85 times 3
Okay.
is 255.
Well,
right?
okay. Right, well, that's why it takes 3 loops.
Well, it's hitting 255. Yeah, but it's not hitting 0.
Yeah.
So yeah, it does throw up an interesting conundrum. But I suppose if we compare it to 1, that would work, because it will. I think. Well, let's see, because it won't hit 1 until the second time around. You see what I mean?
Mm.
I think. Not that you'd ever need a routine like this, but at least it's a kind of fun exercise. But
yeah.
Maybe. Yeah. Okay. So it's hitting the second time around. It's actually hitting 2. Yeah, because it hits 255 and 255 plus 3 is 2.
Yeah.
Yeah. Yeah. I should have known that really. So if you only want it to do it once, that would be every 3. Yeah. But the thing, and I mean, there are multiple different ways of this being quite flexible. I mean, we can also do this, can't we? So we can go dec A, yeah, and ret Z, and so it'll now go backwards because it'll start at 255, right? So it'll go from one way to the other. So I guess it should work. Yeah. And it's starting.
There's a dot.
There is
at 0, isn't there?
There is, and why is that? Because my x starts at 0 when we should tell it to start
0.
at 255, right?
Yeah. Yeah.
I'm still getting that dot, which I definitely shouldn't be getting. Maybe I didn't. Did I compile it? Maybe I just didn't load it. Huh. Why am I getting that dot?
Don't we need to change the pop pixel?
Oh,
the address of
pop
pixel.
Yeah, of course we do. Yeah, because we're starting. I don't need to change it here.
Oh my god, I just understood something.
Yeah, you did. Well done. Yeah, because it needs to be here, right? not where I was changing it. Well done. Yeah. There you go. A little moment of epiphany for you there. Good. Right. Exactly right. Good. Just like that. Yeah. Good. And yeah, I mean, you can mess about with this kind of thing. You can just kind of say,
yeah.
What else could we do here?
Although we've gone away from, so we don't really need. What is my X doing at the minute then?
Well, every time that you see, every time that we plot a pixel,
yeah,
it's just changing the coordinate from 1, 2, 3, 4, 5, right, all the way to 255 or backwards or whatever, right?
Right. So that's just the actual pixel that we're.
Yeah.
Yeah.
I mean, you can do other things as well. You can do like there's another register, which is like.
So if we change that to 7.
You see, what we had before was just, we were just drawing a line, and we were just increasing it each time. So.
Oh, right, I've screwed up. Mine's looping. Oh. Are you there?
Yeah, I'm here, but I don't know what you mean because I can't see your screen. So.
Sorry. No, I added the extra INK, but hadn't changed anything else, so it was just literally looping round and round and round and round.
I see. What I'm doing now, right, is I'm changing it from E. I'm using E instead here.
Okay.
Because I can see that I don't use E again until here, so I can use E. That frees up C, and that gives me that means BC is not being used, right?
Oh God, so you're making big changes, okay.
No, that's a small change. You see here, we were using C register to preserve the accumulator. Yeah. Now I looked down and I thought, well, you know what? I'm using E here, but I only need C up to here, so I can restore. I can use E instead of C to restore the accumulator and then do the calculation, and it means I'm using one less register, right?
Right.
It's common kind of practice that you might look at something like that and say, oh well, I'll use E instead because now BC is free. You know, because I was using C, I won't use C instead. I'll free up BC, right? And the reason I want to do that is because what I'll do now is I'll say something like I'll put load BC in here like this, 0, yeah, and then I'll say load A BC, and then I'll inc BC. Okay, and what should I do? Okay. I'm just messing about here. Right, watch this.
Give me 1 sec. Oh, go on.
Anyway, I've completely messed it up now. I've caused it to freeze. But what I did there, just because obviously we're not just we are facing a non-live audience.
Yeah.
As I said, there's still a mysterious 2 people. Ah, here's Curtis. Spoil, look, joining way late. Certain registers offer specific instructions and operations. Well, Curtis, welcome all the way from sunny Canada. It's well, yes, I suppose yes and no, I guess, right? Accumulator is for most calculations. I think that's the same in almost any assembly, 8-bit assembly. BC, then you've got register pairs BC, DE, and HL, and they can all be used for all the general basic register functions, it can all be used. So they can all be loaded, and they can all be added to and decreased and so on. But B is sometimes most commonly used for a counter, for an 8-bit counter, because there is a specific instruction called DJNZ, which means decrease and jump if not 0, and it decreases the B register and jumps if the B register is not 0. So when you put B, if you set B, say 15, then you can do a loop of 15 by just using DJNZ, and it will the jump is a relative jump as well, so it only needs 2 bytes to make a jump, and it will do everything in terms of decrease the loop and go back and repeat it until it hits 0. So yeah. Incidentally, Andy, I'm explaining things to Curtis in a super fast way, because he's a bit of a whiz coder, so he knows 6809. Not so familiar with Z80, but if I just talk about loops and registers, then he'll know. Yeah, and HL has some special functions in that you can load HL with if you set HL to a memory address, you can load any other register into that address. So you can use load brackets HLA. You can also use load HLB or C or D or E, and even H and L themselves as well. Once you've done that, you'll mess up the memory address perhaps. But if you see what if you did it the other way around. Anyway, it's very late. But yeah, HL is also used for 16-bit addition and a couple of other things. But more or less, those general registers they can be used pretty much wherever. Yes, HL is high-low, but BC and DE are also high-low as well. So you can do add HL DE, you can do add HL HL, you can do add HL BC as well. They all work as pairs. And there's a flag register, and the flag register is paired with the accumulator. So when you're using the stack, when you basically push a 16-bit address onto the stack, then you push HL, DE, BC, but you can also push AF. So you can store your accumulator and all your flag values on the stack as well. Anyway, so Andy, yeah.
Yes.
I think we did all right in the end. You kind of understood more or less how that's all worked.
Yeah.
Maybe I don't want to. At the end of the stream, I just do some like silly random thing, and then when I save it, I come back and I go, "Oh, what have I done there?" So
yeah, I've just taken mine back to where we were just plotting the pixel.
Yeah, that's better. Let's leave it at that. Incidentally, what I was doing was I was getting it to read the ROM. I was getting it to read values from the ROM and use those as the coordinates. So, you'd just get a load of random values from the ROM.
Right.
Yeah. Sorry, just to answer Curtis's question, the flag register would be like our CC condition. Yeah, I suppose so. I mean, there are 8 bits, and I think not all of them are used actually. But the most common ones, and on these streams, we're really only dealing with the 0-bit and the carry bit. So you can test for 0, you can test for not 0, you can test for carry, you can test for not carry. And in that way, that allows you to test for equal to, greater than, and less than, in combination, and greater than or equal to, or less than or equal to, in combination. And those are the main ones. The other ones are to do with, there's one which is like, I think it's half carry, so if you go from one nibble to the other, and one of them is parity, something like that. I think there might be one that checks for positive, or it's a sign. Yeah, no, I'm just checking now. There's a sign flag, so if bit 7 is used for numbers from 0 to 127, and then minus. We can check for that. Yeah, you've got a sign flag, a 0 flag, a half carry flag, a parity, an add subtract flag, and a carry flag. But the ones that you really use all the time in game coding is just 0 and carry, because they're the ones that let you do greater than, less than, equal to. And you don't really need too much more. I mean, of course, there'll be coders with a lot more experience than me that use other flags for more complex mathematical trickery that you might use especially with 3D or something like that, I guess. But drawing lines or different things. Some coders are just really, really good at that sort of thing, but I don't have a lot of experience with it really. And as I said, I've written games and I've never needed to use them. So I am curious what the add subtract flag does. The add subtract flag is used for decimal mathematics to distinguish between the add and subtract instructions. I see. And half carry is used when using decimal mathematics. Yeah, so basically when they design the chip, right, they're expecting that people are using them for converting, as Curtis said there, binary code. I think these are binary coded decimal. I'm not sure, but yeah, binary coded decimal is when you use, if you've got 8 bits and you use 4 of them to use a number from 0 to 9, and then the second one to use a number from 0 to 9. So you're storing decimal numbers within 4 bits each, right? I think, is that right, Curtis? Maybe you'll tell me. I think that's it. But essentially, it's really old school stuff that nobody uses anymore, because at the time people were hard coding things for mathematical calculations. And I suppose, yeah, he's right. It can be used for displaying scores. That's true, especially when memory is really, really tight, right? So yeah, I guess that's another thing to remember, is that when the Z80 was first kind of developed, there weren't very many machines that had a full 64K. A lot of them, because memory is really expensive back then, so a lot of them would have had like 4K or 6K or something like this. So maybe 8K, 8K, something like that, probably. So when memory's that tight, you're gonna want to store numbers in more effective ways, maybe. But yeah, with the Spectrum actually has quite a nice amount of memory, really, compared to a lot of machines of its time. So yeah, there. See, Curtis was saying 16K, $100 upgrade from 16 to 4. Yeah. Yeah. Well, I remember because I had a. He's a big. Over there it was the Coco, but for us it was Dragon 32, right? So I'm sure you remember Dragon 32, don't you, Andy?
Yeah.
Yeah,
I do.
So I had a Dragon 32 before I had a Spectrum, and so I have a little bit of a soft spot for it, and I can even remember. I can remember at the time thinking it would be so much nicer to have a Dragon 64 than a 32, but not that I knew much about how it worked or whatever. But
yeah.
Anyway, it has its appeal, and it has its long-term fans. But in terms of in terms of writing games, I have to say, forgive me, Curtis, if you will, but the graphics modes on it are just not really suited to gaming, to be honest. I mean, the 256 by 192 resolution is just black and white, just without any color at all. And then there's a lower resolution, and it has 4 colors, and the choice of colors is you can either have, I think it's green, red, yellow, and blue, or I think it's something like, or magenta and, oh, I don't know, orange, I think it is, magenta, orange, and it's a horrible combination. So I've no idea why they chose those colors, unless it must be something to do with the graphics chip, and it was easier for them to do those particular colors. It's the same graphics chip that's used on the Acorn Atom.
Right.
So yeah, but when you look at Dragon 32 games, that's why when you look at them, you'll just see this kind of 4-color and really weird choices of colors. But the 6809 chip, the language is really nice, you know. I mean, I think that's probably the reason why people still code with it, because it is really nice in terms of it's got quite a lot of I think it has got 16-bit registers, has it, Curtis, maybe, or something like this? Yeah, it was an older chip. Right, black, blue, red, and white. Ah, so that was you could have 4-color 256 by 192 then. See, in those days, again, you know, we're talking about memory, right? So the graphics memory, as you can see, I mean, it soon adds up. That's the reason why the Spectrum had used attributes. It's one way around it, right? It's quite useful for sort of text and business applications. But memory really quickly adds up once you start adding colors. If you want each pixel to be its own color.
Mm-hmm.
Because if you imagine, like 256 by 192,
yeah,
is going to be that's 48. That would be 48K. If you wanted 1 byte per pixel, right? So that'd be all of the memory of the Spectrum would be completely used up by that.
Yeah.
Of course, if you wanted four bits, then you could halve it down.
Mm-hmm.
And if you want 1-bit color, then you can divide it by 8, and it's 6. Then it's 6K, which is what the Spectrum uses, and then it overlays the colors afterwards using by character square rather than by pixel, which is 8 times 8, which is 64. So it's uses up 1/64 of the memory that you would need.
Right.
Because you've actually got 64 pixels inside the single character square. Yeah, makes sense. So on those old machines, you would have, well, you can read what Curtis is writing as well, but as I said there, look, 320 by 192, 16 colors, that's 30K. That's a huge amount for a machine. Yeah. Well, yeah, absolutely. And if you've got an addressable memory of, say, 64K maximum, then obviously you're going to use up a lot of addresses as well. So
yeah.
Unless the graphics memory can be addressed separately, I don't know. That might be possible. But yeah, so I mean, 16. What Curtis is saying is that the 6809 can do a lot of 16-bit. You see, when we're working here with the Spectrum, it's like a mantra for me. It's like always work in 8 bits whenever possible for speed, right? Because it's an 8-bit data bus, so you know you it's just everything's going to be twice as slow if you don't. But with the 6809 you can do things with 16-bit numbers more efficiently. But the processor speed is also slower, so it all kind of balances out in the end.
Right.
So yeah. Anyway, it's already past 5. Definitely going to knock it on the head now. But we did get somewhere in the end, didn't we? I mean, you know, I hope people who were watching earlier, or rather, people who are watching, I don't even know what they call it. You know, offline, or they're online, but I'm no longer online. Watching the recording, I suppose. Yeah. Sorry it took a bit longer than usual today. As I said, I'm still a bit tired and everything. But we did get somewhere, and let's next time see if we can start plotting on the y coordinate, which is going to be a lot more complicated. But yeah,
that'd be interesting.
All good. All right, guys. Well, look, I just chatted a bit longer there because Curtis very kindly came and popped his head around the door. So, you know, we might as well have just a brief chat and say hello, and then we'll call it a night there. All right then. Well, thank you, Curtis. I'll see you anon next time, maybe. And I'll say goodnight on the stream. Andy, you'll still be here, but
sure.
I'm just
night all.
There. Yeah. Good night, everyone, and happy coding. Bye bye.